The physical pendulum. Physical pendulum has its mass distributed throughout its entire volume. Unlike a simple pendulum, it cannot be treated as an object suspended at the end of a string of negligible mass because the entire pendulum is massive. This could be a meter stick. It could be an elbow. It could be a rod suspended from the wall. Anything with mass that acts like a pendulum. The gravitational torque that arises when the pendulum is displaced from its equilibrium provides the restoring torque that causes the pendulum to return to its equilibrium position. And just like with simple pendulums, the inertia is going to cause the pendulum to overshoot the equilibrium and create this oscillation. The angular frequency period and frequency of a physical pendulum depend on the way its mass is distributed, the distance from the pivot point to the pendulum's center of mass, and the pendulum's rotational inertia, I, around that point. Just as for simple pendula, these quantities do not depend on the amplitude of motion for small amplitudes. For the period of a physical pendulum, using this first equation, if you end up with a weird rotational inertia for a physical pendulum, then you would put the rotational inertia here. In this instance, the rotational inertia was 1/3 ml squared. This is for a rod. And we're looking at half of the length because the center of mass is where the gravitational torque is coming from. So if you end up with this situation, don't forget your rules for complex fractions, where you have a smaller fraction in the top. So that's pretty heavy, so it's going to collapse, and the 3 is going to be in the numerator. And then if you have a fraction in the denominator, then that 2 is going to swing up to the top to get 2 pi square root 2L over 3G.